Hello everyone, I'm Devin Shah and I'm going to present a proposed conceptual framework and overview of predictive bias in natural language processing models. We can think of most predictive models in natural language processing going through this pipeline. We fit our models on some source corpus or population and then we hope they apply to some other population or data in application. In practice, our papers often use random subsamples of the same source and target populations, but the goal is of course that the model can be applied to a new unlabeled target data. In most current methods, embeddings also come into the picture, which can be derived from yet another corpus. Still, in the end, the hope is our models will have good predictions for some target application. However, recently, dozens and dozens of works in natural language processing have shown our predictive models are often biased. Image captioners getting credit biased on the use of pronouns, then pause taggers producing more error for young women. These works talk about a wide range of biases and mitigation techniques. So, how do we make sense of it all? The goal of this paper is to suggest a unified conceptual framework with corresponding mathematical definitions for organizing work on biased predictive models in NLP. But how do we know that the bias exists? We start by considering the distributions of predictions produced for the target population and check if there is a difference or disparity with what is desirable. Building on work from bias in health, we refer to such a difference as a disparity. We then propose that there are two types of disparities which cover most concerns of bias in NLP. First is outcome disparity and the other one is error disparity. So first let's take a look at the outcome disparity. We say that the outcome disparity exists when the distribution of the predicted outcome is not similar to a specified ideal or desired distribution given a human attribute A. As you can see in the graph, this represents the ideal distribution of the outcome variable given a human attribute A, and this represents the distribution of the predicted outcomes given a human attribute A. These two distributions differ, and when this happens, we say that the outcome disparity exists. Now let's take an example. Let's say the human attribute is sex of a person, that is man or woman, and the outcome variable as whether a person will have cancer or not. Since these two distributions differ, we say that the outcome disparity exists in this particular case. Now, let's take a look at the error disparity. We say that the error disparity exists when the distribution of error for at least two different values of A are unequal. As you can see from the graph, this represents the distribution of error in the unbiased scenario given a human attribute A. And this represents the distribution of error in the biased case. As you can see in the unbiased scenario, the error distribution is uniform. And over different values of A, it's equal or similar. In this case, it's not at all uniform and it's not similar as well. So in that case, error disparity exists. So coming back to the walls, Dirkhovy and Sogard noted that syntactic parsers trained on the Wall Street Journal didn't work as well for women as for men. The typical authors of the Wall Street Journal were men. This accounts for error disparity. Hence, the error correlates with the distance in demographics from the typical authors. Although we are talking about discrete variables, this definition allows for continuous distributions too. But focusing only on the disparity doesn't usually provide a solution. It would be like focusing only on the symptoms of a disease rather than its cause. So let's go from the symptoms or disparities backwards in the pipeline to consider possible origins in the bias. First, let's hit selection bias. Selection bias occurs when the source population is not representative of the target application's population. Here, we see the distributions of the source population and the distribution of the target population. They differ. This may or may not lead to disparity when applied. So, continuing with the Wall Street Journal effect, it was observed that the pause taggers and syntactic parsers were trained on Wall Street Journal articles which were mostly written by middle-aged men. Hence, the models didn't perform well on language spoken or written by women or older or younger individuals. We can mitigate selection bias by taking stratified sampling or having some kind of reweighing schemes. So working back from selection bias, a different issue is that labels in the source population are themselves biased, whether from the bias of the annotators or from bad instructions. Here, the difference is between the source distribution of the outcome variable and the ideal distribution of the outcome variable. Let's take an example. In a task of pause tagging, given a sentence or set of words, we need to tag it with the corresponding parts of speech tags. Let's focus on the word out for now. When this sentence is given to the annotators for getting it tagged, for the words getting tagged, let's say I say that it belongs to particle parts of speech tag. But for some other annotator, she would say that it belongs to add position parts of speech tag. So this creates a discrepancy among the annotators, which leads to error level bias in our case. So various ways of mitigating label bias is that we can apply various reweighing schemes, or we can retrain the annotators so that all the annotators are on the same page. So working back from the label bias, we come to model fit, which is where overamplification can take root. This bias origin can occur even if there is no bias otherwise. In order to optimize a cost function, a smaller difference between the human attributes in the source data ends up getting amplified to a larger difference from the model. Thus, the difference between the human attribute for a predicted distribution of the outcome or its error and the source distribution. The source distribution may even be similar to the ideal target distribution, but the fit model can still end up producing the disparity. A prototypical example of overamplification was given by Zhao et al., who noted that the captioning model trained on images of kitchens with women in them 66% of the time ended up captioning women 84% of the time when predicting, hence amplifying the difference which was already present in the source data. We can mitigate amplification by synthetically matching distributions in the source population or by adding outcome disparity in the cost function. So finally, we consider bias in the embedding model, that is semantic bias. This final potential origin is essentially a collection of any of the previous origins, but which may occur based on the embedding corpus and the effect of the association between words in the embedding space. So for example, Zhao et al. Found that the word embeddings contained associations between the gendered pronouns and occupational words. In the example here, female and male pronouns work closer and further to the words associated with pets or to car accessories respectively. So if you're building on pre-trained models, it is important to keep in mind even if you take care of your source data, you might inherit bias from the embeddings. This represents the entirety of a conceptual framework, and we hope others find it helpful for connecting the various work and defining bias in predictive models and countering bias. This is a list of all the countermeasures that can be applied for each of these biases. And also note that each origin has a different source, which can be used to help find different countermeasures. So what are the takeaways? We suggest considering the many potential origins of bias, the embedding model, the feature sample, the fitting process, the outcome sample. If this is of interest to you, please see our paper. The presentation only scratched the surface. We survey many works and countermeasures for each origin. We also detail mathematical definitions of each disparity and origin within the conceptual framework. We see this as a version 0.01 of a unifying framework, and we hope this inspires further work towards ultimately understanding and mitigating predictive bias. These are the references that I've used for creating this presentation, and thank you.